Right, as people start to join in, I'm going to launch a little poll to kick us off. So that should be available to you now. And so just we're going to be talking about heliophysics and Heliolab and the sun. And so go ahead and tell us why we should study the sun. And I know for some of you, you might want to choose an all of the above. It's not there, so choose the one that resonates most with you at the moment.
Yeah, little known fact that the whole reason Andres got into heliophysics was beach vacation planning, and that started his career. Very few people realize that, I think.
Jonathan, I thought we weren't sharing that fact anymore.
Oh, sorry.
All right. Okay, I
Well,
see some
what do you
answers
think?
coming in.
Beach
Did you have?
vacation planning in Bozeman, Montana.
Yes, exactly. Yeah. Very important, Andres.
Wonderful. We'll give just a couple more minutes for people to join us. Please introduce yourself in the chat, your name and where you're joining us from. Maybe let us know if you're a heliophysicist or a machine learning expert or hybrid of both. And then jump into the poll. Let us know why we should study the sun. We'll get started in just a couple minutes here.
Lauren is dialing in, as she says, from the UK. Lauren, you're too young to use a phrase like dialing in, but okay. I have met people who don't know why we say dialing, which isn't a surprise, right? Angelos is nodding his head, going, "Oh yeah, oh yeah."
All right. Well, before Jonathan whips out the rotary phone and shows us the actual dialing in,
I have one
let's.
right here, Ann.
I know you do. All right.
Shall
I'm
we
going
get
to
started?
end the poll and get us started. Just share the results. So looks like we've got people really thinking about our star, the sun being central to all of science, the solar activity impacts the Earth, and one brave person, I'm not sure if this was Andres or not, telling us about the next beach vacation.
No comment.
No comment. Nice. All right, let's go ahead and jump in. So first of all, thank you all for playing along with the poll. We'll find other reasons to study the sun during our discussion today. And I want to hand it back over to Jonathan to officially start us off.
Thank you, Ann, and thank all of you for joining us here today. Today is for you. We are here to talk about the 2025 Heliolab program. Perhaps I'll even say the Heliolab experience, and give you a little information about the FDL network, a network of about 800 scientists worldwide focusing on a variety of domains at the intersection of machine learning, domains such as heliophysics. Today, we'll be hearing from several of our faculty and other participants who have been with us for the last 10 years now since we first kicked off the FDL network. Today, as I said, is about you. So after we've heard from our speakers today, we hope that you will actively engage in questions perhaps about heliophysics research opportunities, as well as some of the specifics around this particular program that we're here to talk to you about today. Again, thank you for joining us, and we'll kick things off today with the Heliolab program director, and that would be Dr. Ann Spalding. Ann, if you'll take us from here.
Thanks, Jonathan. Always so nice to get a formal introduction. So as Jonathan mentioned, this is just a little bit of an overview of what we're going to do today. I'll briefly tell you what is Heliolab at a high level, and then our expert advisors are going to dive into some of the challenges that we might be doing this year. And then for folks who are looking at joining Heliolab for the first time or want a refresher, the last part of the session will go over how the program actually works and what it's like to be a part of our Heliolab community, and then open open it up for Q&A at the end. If you have questions while we're going through, feel free to use the chat and feel free to answer those in the chat. Those are there. We can have a rich discussion in the chat along with the presentations that you're going to see as well. So to kick us off, when we work on Heliolab, we like to set a broad theme, and then from that broad theme, we choose specific challenges that will help us dig into that. And so the broad theme for this year is AI for solar eruptions or solar flares. And this is a photo of one of those, and just for scale, how small the Earth is with those large solar eruptions. We're going to learn a lot more about this from our research experts coming up. And so I would like you to think about what is it that we can do with AI and how can we use that to help us better understand the solar eruptions. And so we've kind of dove into this a little bit already. And one of the things that we're looking at for this year is taking AI and building actually a broader AI approach using a chain machine learning model. And so how can we use that to better model the solar eruptions and understand them? From a heliophysics side, we're looking to advance our understanding of the active region dynamics and flares, maybe form a prediction framework, which integrates a bunch of different variables like state estimation and energy release modeling, and then be able to look at both observational data and physics-based constraints and to bring that forward. From the data science side, this is going to take using a lot of tools from real-time feature extraction, uncertainty, surrogate modeling, ensembles, some of the hybrid AI approaches like continual learning, and really trying to get down to a resilient physics-informed ML solutions. So that should feel amazing and exciting, both from the heliophysics and the data science side. I'd love to spend the next 15 minutes with our experts, kind of digging into some of those concepts on the heliophysics side a little bit, and some previous solutions that we've done with AI and ML. And so we have three expert advisors that are going to be talking to you today. These people have all been faculty, researchers, expert advisors on our teams for many, many years, and have driven a lot of the challenges and amazing results that we've had. And so I'm going to let each of you introduce yourselves and then tell us a little bit about the field that you're going to go into today. And Angelos, you're first. Do you want me to share your slides or do you want to share your slides?
Yeah, please go ahead. So the
All
slides.
right.
Hi, everybody. My name is Angelos Vourlidas at APL, and I'm really a rocket scientist. So I'm coming to this from the space hardware point of view. As you can see here, I work with rockets and also with many of the instruments that we're going to be using data from for this year's challenges. And I have mentor. I was very proud mentor of many PhDs and younger career scientists. So I can talk about pretty much everything about the sun, except for the photosphere in the interior. That's for Andrés to address. And so I'll be talking about why really is the sun so eruptive, and therefore we have this need to understand the eruptions. And so here are some movies showing really how active the sun is, something you don't really see by looking outside or during an eclipse. And so you can see that the eruptions from the sun start from very low down, and they extend out into the solar atmosphere and further out into the corona, and they happen all the time. So the question is why and how we can sort of get a handle on that, on their properties, how often they happen, and exactly how they affect systems and eventually human exploration out in the heliosphere. So in the next slide, you can see the breadth of of data that we have, and that's here is where you compile all the instruments that we have from the stereo satellites. So you can see the sun is now just a little red dot in the center, but you can see that we have multiple viewpoints, and you see some challenges later on that try to take advantage of that, and that the scales of the system go all the way from the sun to the Earth, 150 million kilometers or so. And so the challenge that we have in front of us is how we incorporate all that data and to come up with a better understanding of the solar activity and the eruptions. So where do they start from? I've added this slide because we're going to be talking about flares, and I have some typical examples of very big events that happened in the past. And you can see that for example, the one in the middle, the green and red, that sometimes eruptions happen and they can only be seen in a particular wavelength, right? It's not like a big flare will happen and you can see everything, say, in every wavelength. So that's both a challenge and a key to potentially coming up with better forecasting. And we can talk about how to do that later. But also on the right-hand side, you can see that the flare that we see usually in the X-rays is a bright spot on the sun, but its effects can be global. Again, we need somehow to incorporate small, medium, and large scales into our machine learning approaches to get to the root of the problem. So that's my very, very extremely quick introduction.
And can you go back out of full screen and reshare, please? I just added a quick intro slide. And if you go back to full screen. I think if you go to the next slide. Yes, okay. So I have been with the program for a while now, and I have been part of many teams doing flare forecasting in 2017 and the instrument virtualization and a real instrument that broke in 2018, super resolution in 19, the detection of stellar spots in 20, solar wind structure in 21, neural radiance fields in 22, like making operational the reconstruction of the virtual instrument in 23, and more neural radiance fields in 24. And I think in this moment, one of the things that is most interesting to me in machine learning applied to heliophysics is using AI to do better inversions. There is a lot of inversions that are happening. So the majority of heliophysics data is actually not what we actually want to measure, but it is connected in some way with the things that we want to measure. And so, that's one of the things that we're considering for this year is that the heliosysmic inversion with AI. So if you go to the next slide, in 2022 was the first time that I did work like this. So you may be familiar with neural radiance fields. These are AI algorithms that are trying to learn a three-dimensional structure in space based on planar images. And so if you have different viewpoints of the same object in 3D, then you can kind of guess what the three-dimensional structure is. So if you go to the next, and we did this in 2022 and 2024, working with this, but now for the sun, where we have a three-dimensional atmosphere, and we basically now change the neural radiance field model to do emission and absorption or density and temperature. And then we approximate the structure of the three-dimensional corona using different viewpoints. Now, one of the things that we were thinking about this year, if you go to the next one, is potentially extending this to helioseismology. So it will be like we will be neural velocity fields, right? So we cannot see inside the sun because the surface of the sun is opaque. But the sun is all the time humming like a drum. And it has because it's like you have convection and everything is putting energy on this spherical object. That energy kind of like feeds into these standing waves, and the sun hums, and you can see a representation of them on the right. So you have this sound is traveling between these points, and different frequencies of sound traveled at different depths in the sun. And so by looking at perturbation and how sound travels through the sun as a sphere, you can get an idea of what the internal structure of the sun is, like what you can see on the left. And so the idea is, if you go to the next one, is that we have a variable that we want to measure, which is the three-dimensional velocity inside the convection zone, something we cannot see, but we can see Doppler. Basically, we can see the oscillations of the sun at the surface. So we will use the same way as in an Earth, you can use a mathematical model of how light is emitted and absorbed in the corona. In here, you will use a mathematical model of how waves travel through the interior of the sun. And then, this will be, as these waves travel through the interior of the sun, we can compare at a different point how does these waves look like, etc., etc. And so it follows a similar model as the neural radiance fields, but now is using seismology and velocity and wave propagation to do that inversion. Now, that is basically the spirit of helioseismology. We make this, there are very well established methods to perform these kinds of inversions, but some of them have been long-standing challenges. Some methods use the calculation of a spectrum and fitting that spectra. Some other methods use the propagation of the wave and how long does it take to reach one point to the other. And there is also another method that is looking at spectra but at the surface. And all of these methods are deployed completely independently because just it's a challenge to each one of them has challenges and is not easy to make them compatible with each other. But these are some of the things, the powers of AI, where we can really try to maximize the amount of information that, even if it's loosely and tenuously connected, AI has this way of capturing systematics that could, transform the way we do helioseismic inversions. So that's what I want you to show today.
Yeah, and I'll bring us back to earth a little bit. So yeah, Mike Heyns. I'm also a seasoned FDLer, maybe not quite with as many badges as Andres there. So 2023 researcher, and then last year faculty. My day job is being a researcher at Imperial, focusing on sort of the geospace environment, modeling that and providing forecast and services to the Met's office in the UK, ESA, and others. That's mostly physics-based, but then we also do obviously quite a lot of machine learning on top of that. So what I just want to cover here is maybe through the chain of coupled systems, the impact and why we worry. And I'm here having a bit of a bias towards the sort of geospace environment, but it's more actually where we operate as humankind. So that's the near future is going to be the moon, it's going to be Mars, and a lot of FDL challenges have looked at that. So yeah, as we've heard, we start with those disturbances deep in the roots of the sun that then propagates through this turbulent solar wind, the medium, and then couples to this near Earth space environment and the geophysical environment, and then actually has localized impacts on infrastructure and that. So here around Earth, we have a magnetic field that protects us largely, but that coupling of the solar wind, that plasma environment, generates currents and all sorts of other things that become quite impactful. So potential challenges through this entire couple chain could also include impacts, and I'll just pick out two from previous years. So this was both in 2023, improving it, and then last year actually to some degree operationalizing these models. So the one is a geophysical impacts on the ground, and that's looking at power grids and the effects of those near-Earth current systems that are generated when a geomagnetic storm or that whole bunch of plasma from one of those eruptions comes and hits our magnetic field, setting up currents which then ultimately are induced in the ground as well and entering our grounded infrastructure power grids in this particular case. Another challenge which has seen some fantastic outputs from FDL, just go to the next slide there, thanks, is looking at the thermosphere. So the thermosphere, one of those outer layers of the atmosphere, this region is now influenced, or the density thereof is influenced by geomagnetic storms. And you can kind of see that breathing in that middle animation there of the thermosphere as it expands and goes into the sort of low orbit regime, where on the right, we know we are having more and more satellites populating that LEO orbit, and with more and more congestion in that orbit, there's a greater need to understand what that environment is like and mitigate the effects of an increase, say, in density. So yeah, we really want to avoid collisions that can compound and cascade into something like the Kessler effect, which just becomes inoperable entirely. So there's two examples of ground effects with power grids, and now in space with satellite operations. So there are many more effects that are directly related to those initial disturbances that have their root in the sun. FDL has done a vast number of projects across this. Last year, of course, there was astronaut radiation as a focus as well. We see here the effects on satellites, the power grids on the bottom right, and obviously radiation, a whole bunch of other things one can explore. Just going through to the next slide. I also wanted to highlight that FDL has a fantastic opportunity to look at both the science and the operations, and to have that sort of view on impacts throughout. So understanding what the stakeholders need. And we really found that end users need that forecasting capability. There are a whole bunch of requirements within that. So one of the things you need is fast forecasting. So minimal computational expense at inference, and machine learning approaches are fantastic for that. We obviously want to be accurate, so have that localized driving available. And we need things to be actionable. So that means a sufficient lead time and uncertainty, which you've heard about. Uncertainty is one of the goals this year, but that lead time is really taking everything back to the sun and being able to predict the flares and other driving mechanisms all the way there before they actually impact us on Earth or wherever we are operating. And then lastly, and that was a big thing for last year, the two models, was that they need to be reliable. So we want models that are fit for the future, that can continually learn and be relevant and not just be sort of curated. Underlying all of this, we need the science to tackle that. So there's the operation side, but there's very much the science, and to do the science, we need all of you. So yeah, just on the right is up from last year's model. And yeah, to end off, a little pitch for Carmen. So Carmen was the thermospheric drag model that's had quite a long legacy within FDL. And I would encourage you all to QR this particular code here and have a look at the live website. So that is live. That's actually on SW Trek. And yeah, do see what some of those outputs are. It's not just papers, it's actually outputs in the operational context too. Thanks, Anne.
Wonderful. Thank you, Mike. And thank you to all three of our presenters, giving us just a really much deeper understanding of, one, why we would want to study solar eruptions and how they might be forming from the interior of the sun out to the exterior of the sun, and then what those impacts might be on Earth. And in particular, how we can use AI and ML to really help us understand those phenomena and hopefully move closer towards predictions that will help protect us here on Earth from future solar flares. So I want to right now open it up for some discussion and questions. These are at the moment still what we think we're going to use for our challenges. Those challenges for Heliolab 2025 are being formed right now based off of these types of research that you saw. But yeah, I'm curious if there's any questions or discussion from the audience or from our presenters on some of these ideas.
And while we're jumping into that, Anne, if you have just joined us, please, in the chat, include your name, where you're from, and what your domain is. We're curious to know if you are a heliophysicist or another space scientist of sorts, or if you're a machine learning person, if that's what your particular background is. It would be great to know who we have here with us today. So as Anne said, let's jump in and open things up. and ask if anyone has any comments, questions. And while you're thinking about it, I think it's also important to point out that the examples that Mike used, these aren't theoreticals. As a matter of fact, they're recent things that have been happening. And it is, of course, a big deal. We are in solar maximum right now. The average period for the sun being about 11 years. It's been a very active year for us. We had some significant solar activity just in the last 12 months that has caused all kinds of interesting things to happen here on Earth. One particular company, John Deere, they are the world's leading technologically advanced agricultural company. Their autonomous vehicles were put out of sorts by the activity of the sun, and they had to inform their customers not to rely on the autonomous capabilities of the tractors in the fields. And of course, just a couple of years ago, with thermospheric expansion, Starlink lost a whole series of satellites because of an inability to make reliable, accurate, timely predictions on thermospheric expansion due to solar activity. And these can be quite significant. Mike, maybe you're the one, or Andres, or even Angelos, whoever might want to, while people are thinking about this, give us a quick Carrington event example on what happened 100 and almost 50 years ago now, and how significant that was for the time, and how it affected the then global electric infrastructure, which wasn't much, but it was important. Mike, I see you have your hand up.
Yeah, I was actually going to ask another question, but I can chip in there. So I mean, I was quite interested in the GRCs in my PhD and looking at the actual power network. Obviously, during Carrington's time, there was no such thing, but there were telegraph lines, I believe, that caught fire during that time. So one can just imagine and extrapolate what that could do in current systems. Yeah, my question was actually to Angelos. I love that view you gave on all the different measurements we have and kind of cascading them all together. And I'm assuming, yeah, they're just going to be more and more coming through. And of the future missions, I was just curious which you are most excited about and which sort of data streams you really, I guess, wish you had hands on a few years ago, even.
For the future mission, I mean, we don't have that many coming up. And maybe Punch has been going to be launched this weekend, and so provide more global coverage again of along the Sun Earth line. So out in the heliosphere, but we don't have something so in the oven right now that would give us what I would really need is to have more coverage of the Sun Earth line, sort of behind the sun, right? As we had with stereo back in 2012, when we were able to create those 360-degree maps of the sun, which was sort of we used as our basis for developing the radiance field sort of idea. If we had more of those, I would be really ecstatic, especially now that we have more capabilities, more wavelengths that we can assess. So I'm still keeping my hopes up that we're gonna have some sort of a follow-on to stereo before too long, and eventually, of course, go over the ecliptic. That may be the most exciting thing, that Solar Orbiter now is slowly going above the ecliptic. In March, in the end of April, we're going to be about 17 degrees. Will things look differently from that viewpoint, sufficiently different? I mean, that's a good question. But I suspect that next year's challenge will involve something from, figuring a way to take into account that of the ecliptic viewpoint into our existing workflows.
Thank you, Angelos. Aram, you have your hand up. Please join. Welcome.
Thank you. Yeah. Hi, so my name is Aram, and I'm an analytics engineer, but I used to do some heliophysics programming. And I was curious whether, so I'm seeing a lot of focus on like ML. Has there been any thought about using the actual intelligence, like these models that OpenAI, Google, Meta, X are releasing, are getting smarter and smarter and smarter? Is there any interest in using the actual intelligence of those models to do anything with heliophysics?
Andres, do you want
Great.
to talk a little bit about foundation models and what we might be doing there?
I mean, we are definitely not at the level at which the general intelligence is right now. There is, currently an effort to build a foundation model with all the SDO data. So the SDO is the most rich, like data-rich instrument that we have, like a single observational platform. And so I think, that is a question that has come up before. Like, how do we integrate our data, our current data, with some of those more advanced forms of intelligence? I think, one of the reasons why maybe Anne brought up the effort of the foundation model is that now we can start integrating that at the level of, like, at embedding level with large language models and other forms of intelligence. So it is kind of like, I well, this is my personal opinion, but I kind of see it as a prerequisite step to enable that form of integration. Because in this moment, we are working with very large streams of data, and so, but it is a point that personally it's in the back of my mind. It's something that I think gradually needs to happen, and it will be really interesting to happen. And Heliolab seems like the perfect place to do it. Yeah.
Good question, Aram. And I think it's a good opportunity to mention our partners in this effort. And they have been our partners for the past 10 years. And that would be Google Cloud, NVIDIA, and of course, Pasteur Labs and others have been a part of this journey for some time. And we are very privileged to have access to the resources that those partners bring to the table as we pursue this research. I see, Rebecca, you are here from UCAR. I'm going to put you on the spot because our machine learning experts might not be familiar with UCAR, but we have a very long relationship and deep relationship with UCAR. So if I can put you on the spot, why don't you jump in and just tell us what UCAR is?
Sure. Hi. Sorry, my camera, I tried to turn on my camera, but it says that I don't have camera access. I'm on Zoom for browser, so I'm sorry that it's just my voice. But my name is Rebecca Haven. I work with UCAR, which is the University Corporation for Atmospheric Research. And we are interested in Heliolab 2025. And I am a budget analyst, so I'm just here to kind of get a feel for the program so that I can start making a budget for just for our directorate. But happy to be here.
Well, we're thrilled you could join in. As I said, we are very happy to have the longstanding relationship with UCAR that we have. It is located in Colorado, for those of you who don't know, which happens to be the space weather center of the universe, arguably. So again, thanks for being here with us today. Any other questions from any of you or comments that have joined today about the research that we're talking about? Okay, Anne, hearing none, perhaps we can move on and start talking a little bit about the specifics around, as we started to before, what the FDL network is and what Helio 2025 specifics are for those who are interested in participating.
Absolutely. So just coming forward. The first thing to know is that FDL and Heliolab is a year-long program. And so the point of the program that we're in right now is defining these challenges. And so for the researchers and from both the heliophysics side and the AI/ML side out there, like, we welcome your questions and your input as we take these broad concepts and really define them down into the challenges that we'll tackle over the summer. The summer is our engineering sprint. And I know there's a few folks on the call who have applied for this engineering sprint. If you are wanting to join us this summer as a researcher or faculty, please apply. We are setting those teams up now. The teams will be formed. The interviews happen now through March, and then the teams are formed. And then we go into that 8-week sprint where we're really diving deep into the research. As Jonathan has mentioned, that sprint is supported by Google Cloud with a wealth of compute that allows us to do these AI and ML solutions. And then our faculty and experts who have been studying this for many, many years and really help to guide the teams on their process. After that sprint, we move into our communications period. So in the fall, we present our results at various conferences like AGU and NeurIPS, and we also put things out for publication. So year-long process with that 8-week sprint being in the center of that. A little bit more formal timeline you can see here. So again, for those of you who are interested in joining us, our applications close on 31st of March. I'll put the website for that in the chat, or Gabe will. If you are thinking of applying, please do. We have a lot of great people who join us every year to form the teams that do this research through our summer sprint. So a little bit about how FDL works, and I know I'm speaking to the choir for many of you who have been part of our teams before, but for those of you who haven't, it really works because of the community and because of the team. So when Andres put up his slide and showing the last 10 years of challenges that he'd been in, and you see a little bit of the fun that we have in making our team slides, that ability to form a team that is a combination of our faculty, our researchers that are either domain experts or AI and ML experts or some sort of hybrid between them, and really well-defined challenges, all working together. So a lot of the times our challenges are integrated. And so something that one team is learning or the way that they're working with data can help another team. They're also integrated back through the years. And so the research that we've done each year helps us drive the research forward the next year, and you get to take advantage of that. And then sitting at the center is our support team. And so just to introduce us real quickly, you'll see our names often, but the Heliolab support team running the program is myself and Gabe Sutherland, who's on this call. Helping us build effective teams and community is Belina. On the outside of this, our director, of course, is James Parr, who's on the call, and Jonathan as our exploration director. And then we wouldn't be able to produce the types of amazing videos and results that you've seen in this presentation without our design team. And of course, we wouldn't be able to keep running without our HR and operations team. So you will hear from all of these folks throughout the program, but just wanted to give a shout out to them now.
And that culture piece is so important that you're about to talk about. I want everybody to go back later and look at the pictures that Andres showed in his presentation of the teams over the years. That speaks to what you mentioned, that they continue to work together, that this network is definitely generative over time. But did you notice how they got cooler looking over the years as well? Let's face it, heliophysics is very cool, but Andres, you guys got so cool looking by the last team photo. I can't wait to see what you guys look like next time. So culture that Anne's about to talk about, very important to us.
Yeah, thanks, Jonathan. Yeah, just kind of digging into it more. So being able to do this research means we have really smart people, and we have compute, and we have data, and everything is set up. But really, at the end of the day, it means we're building strong teams. And that's at the heart of what we do with FDL. And so culture, we're talking about the spirit of collaboration and working together, a respect for the product, a respect for each other. And we build this into the program very, very deliberately. We have something called our 6 C's. We have our collaboration coach, Belina. We have people who've been working with us year over year who really understand how to build that team dynamic so that you as researchers can come in and be successful. You can work together collaboratively. You can work at amazing speed and create some really great results. Heliolab is a virtual program. It has been for the last 2 years and will be again this year. We occasionally have some in-person components, but we still create community virtually. So we have a stand-up every day. We start the day off with a stand-up. Everybody comes together as a community. We help each other get to know each other as people through our bio sketches. This astronaut playing accordion is because Andres also gave us some accordion during this summer. We help people get to know each other through their skill sets. So we share our AI, ML, and domain expertise across the teams. We also have a little bit of fun in real life. This last year, everybody got sunflowers and Lego kits to be able to kind of energetically interact with each other in their teams. And then, as I mentioned, sometimes we come together. So this is last year's team at our technical research presentation in October. And so we all got to be in person for a component of that as well. Yeah, can't overemphasize how much the culture really makes this something different than you may have seen in previous research experiences and really lends to the success.
And what is cooler than accordion? Right there. I mean, that says it all right there.
Anyone else want to jump in on the culture or the team dynamic that we create before I go forward?
It would be great to hear from our three speakers or any of our past participants on what they think of that. As Anne said, we celebrate all those things. We sincerely believe in and are committed to a mindset of generative creativity in these teams. And it really pays off, especially when we think about the long term over the years. Is there anybody past participant who'd like to chime in on that before we move on?
Another quick 2 cents in there. Just, yeah, I cannot rave enough about this and the community aspect. So it's obviously the teams who are busy with the sprint, but I think the culture goes much wider than that. And there was alluding to it earlier, I think, Jonathan, where you said about 800 or however big that community is. And yeah, it's so great to be able to tap into that. That larger sort of hive mind, and especially when you're in the thick of it, there's always someone to talk to and solve a problem on the fly. And I think, yeah, and it stems from the culture and that openness as well. So absolutely love that aspect.
Thank you, Mike. Anyone else on that point? And we're going to move on right away if not. Okay. I think he said it all.
So all of those things together, so the challenge definition, our support from Google Cloud for Compute, our expert advisors, our culture, all leads us to really, really successful results. And so we love to put up this slide, which is our 50 AI first. This is over the course of the 10 years of FDL, both in Europe and in the US. But we are continually pushing the boundaries on what we can do for research, getting publications, presenting at conferences, winning awards, all of those things because of what you all bring to the program and the way that we've set up that structure to be successful. So this is just a nice way of showing the end result of that type of research. All right. So I want to open it up to Q&A in a second, but I also want to just point out that there's a lot of resources available for everyone to learn more about the program. So heliolab.ai will take you to all of the Heliolab resources. And on that, you'll find our technical results and findings from our 2024 program. So the 4 challenges that we did there, as well as previous years. And then our opportunities document, which talks a lot more about what we're going to do with this program and how we're going to go forward. So both of those things are available there, as well as application information. The website again for applying, fdl.ai/apply. And then just a couple of details. So applications close on March 31st. There are also applications for our other sister programs. So this is Heliolab, but we have in Europe running also Lunar Lab and Earth Systems Lab. So this year we've really focused on getting each of our 3 programs to have a solid theme. So of course, the Earth, the Moon, and the Sun. And those applications are available on the same website. This is a program for PhD and postdoc level researchers. It is paid. It is the sprint, which is the full-time component of it, runs from mid-June to mid-August. And as I mentioned before, we have a lot of published results. We work with a lot of great industry and government institutions to get us to those results. And I think that is it that I have. I did want to open it up and see if there were any questions from anyone around the program or the logistics going forward.
Please feel free to raise your hand or ask your question in chat if that is your preference. While you're thinking about that, we sincerely hope that you will consider applying. We sincerely hope that you will apply. And keep in mind, this session has been recorded. And so if you know of other people who may be interested in being part of such an impactful community of scientists, researchers from around the world, please share this recording with them. Perhaps you'll find a buddy that you want to apply with and perhaps even collaborate together as we go forward. We want you to be a part of us on this journey.
Great. All right. With that, I'm going to give us all a few minutes back in our busy days. Thank you again sorry. There is
Aram just raised his hand. Aram.
Oh, no.
I think that was a wave.
It was a wave. Sorry. Okay.
Clapping.
Sorry to interrupt, Anne.
But Olga did raise her hand. So Olga.
Okay.
Yes, I did. Hi. I'm not a young PhD or postdoc, but like a senior scientist, I have a question for the future. What do you think your topic is going to be next year? It's because this year you selected flares, solar flares, but do you create a pool, or how you decide on the topic?
Yeah, it's a great question. So throughout our summer sprint, we invite expert advisors from throughout the scientific community to attend, to watch all of the challenges, to give feedback. So Olga, that's a great place where you might want to join us. And in that process, there starts this germination of discussion of what's next. And then as we get to the end of the engineering sprint and start publishing these results out at our NeurIPS and our AGU conferences and elsewhere, again, that conversation continues to bubble up. And then in the fall and early spring, we host things called the Big Think, and we open this up to a wide variety of scientists and give them some hunches about what we might study, but we get a lot of input there in terms of what's a great thing to do next, how do we build off of previous results, what's really pressing for us to learn and understand. So I don't have a crystal ball and don't have the answers to what might be next year. I don't know if anybody on the call wants to jump in and say, but we definitely have that as a community engagement piece and really invite our scientific community to help us form those each year.
Okay.
Yeah.
Thank you. Invite
Thank you.
me
Great. Great
do.
question, Olga. Thank you.
All right. I will give one more opportunity for burning questions if anybody has them. And of course, if you don't, feel free to reach out to us over email. We can definitely answer any of your questions there. And Jonathan, anything else you want to say before we head off?
No, other than, of course, we're all open to you connecting to us on platforms such as LinkedIn. If you'd like to also stay in touch that way, you can follow the FDL LinkedIn accounts and the Trillium LinkedIn account to stay connected.
Wonderful. Thanks, everybody. Have a great rest of your day, and we look forward to hearing from you.